Now in this question, we are given that a biomechanical research has shown that when a 67 kg person is running, the force exerted on each foot as it strikes the ground can be as greater as 2300 Newton. Okay, now there are three parts that we need to solve. In the A part, we are asked to find the ratio of the force exerted on the foot by the ground to the a person's body weight. So person's body weight, we have mg. M is 67 kg and G is 9.81, and the force exerted by the ground on the person is given to be 2300 Newton. So the ratio will be, or we can write F over W. F we have 2300 Newton, mg we have 67 times 9.81, which is equals to approximately 3.5. So this is the ratio and the answer for the A part. Next he says that the only force acting on the person is, the first one is the force exerted by the ground, and next one is the person's weight, and then we have to find the magnitude and the direction of person's acceleration. So let me draw the free body diagram. So here we have the weight force mg for the person in the downward direction and the normal force in the upward direction, let it be F. Now we have to calculate the magnitude and the direction of the person's acceleration. Okay, so a net force, we know it is equals to mass times the acceleration. Now net forces, this direction I am taking positive, so F net we have equals to F minus mg, right? So we can write by Newton's second law of motion that F minus mg will be equals to m times a, right? And from here the acceleration, this is basically acceleration in the vertical direction or in the y direction, so we can write ay here. So this will be equals to F minus mg over m. Now we can put the values to find the acceleration ay, and that will be equals to F we have 2300 Newton, mg is 67 times 9.81, and then divide by mass is 67 kg, and on solving you'll get this value to be 25 meter per second squared, and the direction is in the upward direction because it comes out to be as positive, that is why upward. Now next in the C part we have to find that if the acceleration found in part B acts for 10 milliseconds, then what would be the resulting change in the vertical component of person's velocity? It's pretty simple. Acceleration, we know it is change in velocity over time. So from here, change in velocity, this is along the y direction, so this is equals to ay times t. Now change in vertical direction is equals to ay we have 24, and time is given to be 10 milliseconds. We can convert it into seconds by multiply it with 10 to the power minus 3, this much of seconds, and on solving you'll get this value to be 0.25 meter per second. So this is the required answer. Now in this question we are given that on an aircraft carrier a jet can be catapulted from 0 to 155 miles per hour in just 2 seconds. So initially it have zero velocity and it increases to 155 miles per hour in just 2 seconds. This is what we are given. Now if the average force exerted during the process is 9.35 times 10 to the power 5 Newton, then we need to find the mass of the jet. So if we draw the free body diagram for the jet, the only force in the direction of motion is this F. Its magnitude we have 9.35 times 10 to the power 5 Newton. And by using the Newton's second law of motion, we can write that this force F will be equals to mass times acceleration. And from here, this mass will be equals to force divided by acceleration. We have the value of force, but we don't have the value of acceleration. So for that we can use the given data. So the average acceleration will be equal to the change in velocity over change in time. Change in velocity we have 155 miles per hour. Now we have to convert the unit in meter per second. So we know that in 1 miles we have 1609 meter, right? And in 1 hour we have 3600 seconds. So if we have converted the unit into meter per second, divide by delta t, we have 2 seconds. Now if you solve it for the average acceleration, it comes out to be as 34.6 meter per second squared. Right, now it's pretty simple to calculate the mass. You can put the values here. So mass will be equals to force, we have 9.35 times 10 to the power 5 Newton divided by 34.6 meter per second squared. And after solving, you'll get this value to be 2.70 times 10 to the power 4 kgs. So this is the mass of the jet. Now in this question it is given that an archer shoots an 0.024 kg arrow at a target with a speed of 54 meter per second. And when the archer hits the target, it penetrates to a depth of 0.083 meter. Now there are two parts that we need to solve. In the A part, we need to find the average force exerted by the target on the arrow. Okay, so this direction I'm taking the positive x, the direction of motion, and average force. So if you calculate the average force by using the Newton's second law of motion, we can write that net force will be equals to mass times acceleration, right? And we have only one force in along the x direction is F, and it is equals to mass times acceleration, right? We are not considering the drag force. So if we are able to calculate the acceleration, we can calculate the force exerted on the arrow. So first we will be calculating the acceleration. So acceleration, we have the final velocity minus the initial velocity divided by 2 times delta x. We have just used the kinematic equations here. Now the final velocity goes to 0, and initial velocity we have 54 meter per second, and penetration, this delta x is the penetration distance, which is 0.083 meter. So if you put the values, and it should be square, should also be there. So minus vi square is 54 meter per second and its whole square, divide by 2 times delta x is 0.083 meter, and this value comes out to be as 175.6, and the unit is meter per second squared. Now it's very easy to find the force. So force will be mass times acceleration. Now mass for the arrow is given to be 0.024 kgs, and the acceleration, this should be negative sign, should also be there. So minus 175.6.2 meter per second squared. So on solving, you'll get this force to be negative 0.42 kilonewton. So this is the force and the answer for the A part. Now next, in the B part, it is given that if the mass of the arrow is doubled and the force exerted by the target on the arrow remains the same, then by what multiplicative factor does the penetration depth changes? So what it says that this force remains the same, mass increases by 2, then what would be the change in this delta x? Okay, so if this force remains the same, mass becomes 2, then acceleration should becomes half, then only this force would remain same, this 2 and 2 will cancel. So if acceleration becomes half, if this acceleration becomes half, then from here this delta x, this will be equals to minus vi square over 1 over 2 times a times 2, and this 2 I'm taking in the numerator, so I've taken like this. So if you see this value, this is the initial delta x initial, and this is the delta x final. So this becomes 2 times the initial value. Therefore, for the B part, the penetration distance increase by a factor of 2. So this will be the answer for the B part. Now it's a science fiction question. It says that if the Tyrannosaurus tripped and fallen, the ground would have exerted a normal force approximately 260,000 Newton on its torso as it landed, and the mass is approximately 3800 given in the question. Now there are two parts that we need to solve. In the A part, we need to find the magnitude of the torso upwards acceleration as it comes to rest. So if you draw the free body diagram of torso, we have the mg force in the downward direction and the normal force in the upward direction, right? And net force we have equals to n minus mg. This is the net force, and this is the acceleration in the upward direction. Now by the Newton's second law of motion, we can write that n minus mg will be equals to mass times acceleration, and from here a will be equals to n minus mg divided by m. We can put the values to find the upward acceleration. So normal force exerted is 260,000 Newton minus the mass for the Tyrannosaurus is 3800 kgs times g is 9.81 divided by mass is 3800 kgs, and if you solve it further, you'll get the acceleration to be equals to 59 meter per second squared, which is nearly 6g, 6 times of g. Okay, this acceleration is huge. Now next it says that assume that torso is in free fall for a distance of 1.46 meter as it falls to the ground, then by how much time is required for the torso to come to rest at it contact the ground. Okay, so when it was in free fall, suppose this is the ground and it was in free fall to a distance of 1.46 meter. This is given in the equation. So here at this point, let the velocity be, initial velocity be 0, and here the final velocity becomes under root 2gh. Right, we have just used the equations of motion in the vertical direction and we have obtained this equation. So this value will be equals to under root 2 times g is 9.81, height we are given to be 1.46, which is equals to 5.35 meter per second, right? So when it is just on the verge of falling the ground, it has this much of velocity. Now after falling on the ground, suppose it penetrated with some distance, and here the velocity becomes 0. Here the velocity is 5.35 meter per second, and here the velocity becomes 0, and acceleration during this time is 59 meters per second squared that we calculated in the A part. So time taken by the Tyrannosaurus to come in rest, t, this would be equals to the change in velocity over the acceleration. So change in velocity will be 5.3 minus 0, this is 5.3, and acceleration we have 59 meter per second squared, and this is meter per second. So from here this time comes out to be as 0.091 seconds. So in just this much of time the Tyrannosaurus comes to rest.